Good morning. We are ready to start gravity. You thought you were going to do that the first thing when you came into Physics 4a, didn't you? But we finally squeeze it in the last week of the quarter. Gravity. And then I just want to point out, this is the last week of the quarter. So if you're like me, you're getting a little burnt out. It's been a long quarter, been working hard, and just keep your eye on the finish line, okay? 1 week of classes this week, and then finals week is next week. So stay focused, finish strong, and then there's plenty of time to recuperate after that, okay? Finish strong. Up until now, what have we been using for the force of gravity? Mass times the acceleration of gravity, right? mg. But this is only true on the surface of the Earth. We need a rule that works anywhere, right? Because gravitational forces can exist anywhere. It may be on the surface of the moon, some object interacting with the moon, maybe the moon interacting with the Earth interacting with the sun, or any two objects. You and I walking past each other when we walk down the hall interact gravitationally with each other, right? Any two masses interact gravitationally, and we need to understand that. Luckily, Isaac Newton figured it out. He said the force of gravity is proportional to, what would the force of gravity be proportional to? Let's think about it for a second. We've got two masses, M1 and M2. What would the force of gravity be proportional to between these two masses if these two masses were interacting with each other? It would depend on what? The masses, right? M1, it would depend on M1, and it would depend on M2. It would be proportional to M1, and it would be proportional to M2. That means it's proportional to M1 times M2. And it would be affected by the distance between them. As they move farther apart, the force gets weaker and weaker and weaker. It's an inverse relationship, and it's an inverse square. It goes as 1 over r squared. Of course, we want an equal sign here, right? We want an equal sign right there. So we need a proportionality constant, capital G. So this is our universal law. Means it works anywhere. Any two masses, anywhere, this holds true. And the force of gravity is a small force. It's a very weak force compared to some other forces out there. G is a small number, 6.67 times 10 to the negative 11 in SI units. Newton never knew what G was. He figured out the proportionality, but G is so small they couldn't calculate it until years later. Somebody developed an apparatus so sensitive they could figure out what G is. All right, we've got our universal law of gravity now. Well, we've got a universal law of gravity that we say is true anywhere, anywhere. And we have a law of gravity that we say is true on the surface of the Earth. Well, the surface of the Earth is anywhere, right? That's someplace. So these two formulas must agree on the surface of the Earth. let's take a look and see what we get. You get the force of gravity is G times the mass of our object that's sitting on the surface of the Earth times the mass of the Earth, right? The other object is the Earth. And what's the distance between them? The radius of the Earth, right? If we're on the surface of the Earth, if we have m have some object here, that object is probably pretty small compared to the surface, the radius of the Earth, right? So they're the distance, the radius of the Earth apart. Now, you may have noticed, what distance did I use here in the formula? The distance between the center of masses of these two objects. That might not be obvious that you can do that. In fact, Newton had to invent calculus to prove that that's the same thing. When you're outside of this mass distribution, because it's spherically symmetric, when you're outside of it, it's as if all the mass is at the center of mass of the object. We can treat it like a point mass. Newton was a busy guy. Laws of motion, law of gravity. He invented calculus. He did a lot of work with light. Yeah, busy guy. All right, and what does this have to equal then? If these two formulas have to agree on the surface of the Earth, this has to be equal to mg, right? So we can cancel out the mass of our object. And what do we get? We get that G is equal to little g. The acceleration of gravity is equal to our constant, universal gravitational constant, capital G, times the mass of the Earth divided by the radius of the Earth squared. And if you remember this, which I know you will, you can calculate the acceleration of gravity, little g, on any planet. You can calculate it on the moon using this exact technique. You can calculate it on Mars. You can calculate it anywhere, because you can equate this. This one is always true. And then you just set that equal to m times the acceleration of gravity on that planet or on that moon, and you can solve for the acceleration of gravity there. All right, so gravity is the one force we have in physics 4a that can reach in from a distance and impact something else, influence something else. Everything else requires some type of contact, right? Even though maybe there is no such thing as contact on a microscopic level, but on a macroscopic level, there's contact there. Somebody comes up and pushes on your arm and you feel that, right? That's a force. We can understand that. That's something we can wrap our minds around. But something reaching in from a distance. If your friend was across the room and went like that and you felt a force because of it, that would be kind of surprising, right? But that's what the Earth does. You step off of a chair and the Earth pulls on you, pulls you back to the surface of the Earth without touching you. And we have to kind of figure that out. We have to wrap our minds around that. We need some way of comprehending how objects might exert forces on each other without touching each other. Our model, we have a model for that. A model is something we use in science to help us kind of wrap our head around something, to help us picture how something might be. Sometimes our models are correct, sometimes they aren't. But as long as they're helpful, that's what's important. Even if a model is not completely accurate, if it's helpful in helping us picture how something might be, helps us understand something, then it's useful, and that's what's important. Okay. Our model is fields. What we say is that a massive object fills the space around it with a gravitational field. And any other object with mass interacts with that field and feels a force because of that interaction. So these are our field lines. And what direction do they point? They point the direction a mass would go if we put it at that location. So if we put a little piece of something here, some little massive object there, what direction does it go? It goes this way, right? Gravitational force is an attractive force. We only have one kind of mass, one kind of mass, and it attracts other mass, right? So this object would feel a force in that direction. It would move in that direction. So that's the direction the gravitational field points. It points the direction a mass would go if you put it there and let go of it. Now, what's next? Potential energy. And what have we been using for potential energy? Because we're on the surface of the Earth, and when we're on the surface of the Earth, what do we use? We use mg as our force of gravity. Excuse me. On the surface of the Earth, force of gravity is mg. What do? We find the work done, right? We say work is the integral of f dot dy. We're going to lift something up, let's say, right? Lifting something up. We want to know how much work does gravity do when we lift something up, right? Something like that. Well, we plug in mg. We get the integral of mg dy is mgy. I think there's a minus sign somewhere because of the direction. Gravity points down, we're going up, the dot product. So we get this, we get and what we say is that this, let's let this equal UG. And that means that we always get negative delta U for the work done. Anytime we have a conservative force, we see that the work done only depends on the endpoints, where we end up and where we started. How we got from the endpoint to the starting point didn't matter, right? The only thing that ends up in the equation here is where you started and where you ended. That's true anytime you have a conservative force. Force of gravity was the first one we saw, and we said that this, we'll just call this mgy, we'll just call that gravitational potential energy. And the work done by gravity is negative delta U, the change in gravitational potential energy. The second one we saw was spring potential energy. Spring potential energy also is a conservative force. And the next one you're going to see is in physics 4b is the electric force is also a conservative force, and we're going to get electric potential energy. So we said U sub G is mgy, but again, we said this because this is only true when F sub G is constant. On the surface of the Earth. Now we want to know, well, what in general, what's gravitational potential energy? What if I threw something up into the air on the moon? What if I have two objects floating around in space and I want to use energy to find out how fast they're moving when they crash into each other? Well, I need a general form of gravitational potential energy. I'll take my force. I know the general form for the force. Gravitational force of attraction between any two masses, m1 and m2, a distance r apart from each other. This is our formula. Some textbooks will try to write this as a vector equation, and it's kind of confusing. They define a vector from one mass to the other one, and just use it to get the magnitude of the force. You know, two masses always attract each other. If this is mass 1 and this is mass 2, the forces are this way, right? The mass on 2 from 1 is toward 1. The mass on 1 from 2 is toward 2. You can figure out the direction pretty easily, right? Just use this equation to give you the magnitude of the force. Now let's find the work done. Work done is the integral f dot dr. We'll plug in our force. This is in moving something from some initial place to some final place. And what do we get? We get a not squared, no. We get a negative 1 over r. When you integrate 1 over r squared, you get negative 1 over r, and then you evaluate this. I think there's a minus sign because of the direction we're moving. And we say this must be, let's call this only depends on the final position. This only depends on the initial position. It doesn't matter how we got from the initial to the final place. All that matters here is where we started and where we ended. Let's call this gravitational potential energy. And what does work have to be? Negative delta U. Did I get negative delta U here? So what is U then? U must be, it's actually the opposite here. I'm going to get rid of this because there's a minus sign there. Minus G M1 M2 over R, not R squared, over R, 1 over R. This is in general. Any two masses anywhere in the universe, this is our formula. All right, does it make sense? Let's think about it for a minute. Do we need that minus sign? What's going on here? Does it make sense? Let's just plot what this looks like. If we plot UG versus distance, what does a negative 1 over R look like? It looks like this. That's negative 1 over R. And what has to happen as these two objects become closer together, the potential energy, gravitational potential energy, has to go down. When they get farther apart, the gravitational potential energy has to go up. Does it work? Yes. With the minus sign there, it works. So we get the minus sign. When you integrate, it naturally comes out. When you integrate 1 over R squared, what do you get? Negative 1 over R. It naturally comes out of the equation. But if you think about it, it has to be there because otherwise the gravitational energy wouldn't make sense. As the objects became farther apart, if this was just a 1 over R, if that minus sign wasn't there, this is a 1 over R relationship, right? As the objects become farther apart, as R gets bigger and bigger and bigger, the gravitational potential energy would get smaller and smaller and smaller. That doesn't make sense. We know that gravitational energy increases when we get things farther apart because there's more distance for them to move and move, and they're going to be going faster and faster and faster. And the bigger the distance that force acts on them, the more energy they're going to have, right? So this doesn't make any sense. But the one up here does. As the objects get farther apart, the gravitational energy gets bigger, right? A negative 2 is a bigger number than negative 5 when we're talking scalars, and energy is a scalar. Negative 2 is bigger than negative 5. 0 is bigger than negative 2, right? So the gravitational energy is getting bigger as R gets bigger, as the objects become farther apart. And as the objects become closer together, as R gets smaller, the gravitational potential energy gets smaller. It becomes more and more and more negative. Maybe we just need to do an example. Let's do a quick example here. How we use energy. How fast does a projectile need to be launched from the Earth's surface to reach a maximum height of 1 Earth radius? And we are going to ignore air resistance. So let me draw a picture of what's going on here. We have the Earth. We are going to launch something here. It's going to go up and come back, right? And we want this distance to be equal to an Earth radius. You have to think about problems like this. On the final exam, you're going to get problems. All of a sudden now you're going to have to think about it. Does it, what approach do I use here? Can I use my kinematics equations? Can I use, energy? Can I use, you have to think about the distance here. If you want to go 1 Earth radius away from the Earth, are you still considered close to the surface of the Earth where G is constant? No, you're very far away from the Earth at that point, right? Very far away from the Earth. So you can't just, you got to think about distances here and say, whoa, wait a minute, I can't assume I'm on the surface of the Earth if I'm a whole Earth radius away. I've got to use some other technique. I've got to use my chapter 13 technique here, universal law of gravity, where gravity can change over distance. All right, so how do we do that now? This is an energy problem, right? You'd probably use energy to do it. Just don't fall into the trap of using a constant, using mgh as your gravitational potential energy. That would not work here. If we ignore air resistance, then all of our mechanical energy at the beginning is equal to all of our mechanical energy at the end. All right, so initial mechanical energy is a combination, right, of kinetic and gravitational potential. And at the end, it could be some combination of kinetic and gravitational potential. Are we moving at the beginning? Yes, we launched this thing with some big speed initially. So lots of initial kinetic energy, 1/2 mv initial squared. Are we moving at the end? No, that's the highest point, right? That's where it comes to rest, at the highest point. So we've got no kinetic energy at that instant. Now here's the first change from how we used gravitational energy in the past. In the past, we could pick any point we want to be 0 because it was a linear relationship. Where was our relationship? Here, oh, right here. Because we had a nice linear relationship, it didn't matter where 0 was. Any 2 points would, no matter where we define 0 on a straight line, right? No matter where you define 0, the difference between any 2 points is always going to be the same. But this relationship is not linear, right? This is not a straight line here. So this does matter where we define 0. We don't have a choice anymore. We can't say, oh, let's let the surface of the Earth be 0, or let's let our final position be 0, or initial position be 0. We have no choice. There's only one place where it can be 0. When r equals infinity. When r equals infinity. That's the only place we can have zero gravitational potential energy, when the objects are infinitely far apart from one another. So in our problem here, we start out with the object on the surface of the Earth, and it goes until it's 1 Earth radii above the surface of the Earth. Are they ever infinitely far apart? No. So we cannot have zero gravitational potential energy anywhere in this problem. Initially, the object is on the surface of the Earth, so they're 1 Earth radii apart, and at the end, they're 2 Earth radii apart. So that's the first issue. Don't forget that. We can't define zero wherever we want. It's only zero when r equals infinity. And the second thing you have to remember is the minus sign. Gravitational potential energy is negative, so we need our minus sign here. Minus G, M Earth over R Earth. And at the end, it's minus G, M Earth over 2 R Earth. Okay, so those are the 2 important points. Now we just finished the problem. We get V is G M Earth over R Earth square root. It's a big number. It's a big number. You just have to keep track of which m is which, because in this equation, it doesn't matter. You have an m1 and an m2. Call one of them the mass of your object and the other one the mass of the Earth. Doesn't matter which one's which in this equation, right? But in this equation, it does matter. 1/2 mv squared, that's the mass of your object. And it cancels out. It cancels out, and you're only left with the mass of the Earth. So just as long as you remember which mass is which, it's a good idea. Yeah, in this equation, doesn't matter which one's which. They're just multiplied together. But this does matter. That's the mass of your object. What's moving, right? What has the kinetic energy? Now, we can take this sort of one step farther and define something called an escape speed. This is a big number. And even though we launched this object with this big velocity, it still eventually got to some point where it stopped, turned around, and came back to the Earth, right? What we're wondering is there some speed we can launch something with from the surface of the Earth such that it does not stop and turn around and come back to the Earth? It leaves and it never comes back. That's called the escape speed. The 2's cancel out. It should be, I think this is correct. There's a 2 in the numerator, there's a 2 in the denominator. I just canceled them out. But you can double check me. I should say you should double check me. Escape speed. What does that mean? Escape speed means that our object comes to rest just as it gets to infinity. Does that make sense? If it stopped before it got infinitely far away, there'd be a little bit of gravitational force acting on it, pulling on it, and it would eventually end up coming back to the Earth. So escape speed, we want V final to be 0 at r equals infinity. Let's see, we I added this to both sides. That gave me a positive 1/2 on this side, right? Negative 1/2 plus 1 is positive 1/2. And then I have a 1/2 over here, and they cancel. This is, maybe you're forgetting, this is 2r down here. This number is half as much as this number. We good now? So we'll do the same exact problem again. Same exact problem. Instead of throwing it up, instead of figuring out what is V initial such that this object makes it up to 1 Earth radius, turns around and comes back, we're going to say, what is V initial such that this object comes to rest at infinity? And it's never, if it's at infinity, it's not going to come back, right? Sort of. Initial kinetic energy, 1/2 m V initial squared. Final kinetic energy, zero. We want it to come to rest at infinity. Initial gravitational potential energy, don't forget your negative sign. G, M, M Earth. We're launching from the surface of the Earth. We are finding the escape speed from the Earth. Final gravitational potential energy, zero. It's the only time, you can set gravitational energy to be 0, when the two objects are infinitely far apart from each other. And I know it's weird to say that the object gets to its biggest, it gets to its biggest gravitational potential energy. It gets to 0. Yeah, 0 is the biggest it's going to get. And it always has less than that as they get closer together. Negative, because negative numbers are less than 0. Energy is going to be conserved. It ends up with 0 energy. It has to start with 0 energy, right? So that means that 1/2 mv squared must equal Gmm over r. Doesn't matter what the mass of our projectile is, right? That cancels out. We get the square root of 2 times what we got earlier. It's a big, big number. Is that what we do when we launch stuff? When we launch rockets? No, we don't just give it one big push, some huge speed, and let that carry it all the way out until it gets to wherever we want it to go. We have a rocket with fuel, and it doesn't have to launch with a huge speed because it keeps pushing, right? It's not just one push we're giving it. It has that fuel that it's burning, and so it keeps going and going and pushing and burning fuel, and it doesn't have to be launched with some incredibly large speed to make it into space. Why do we launch rockets from southern Florida? Where's the best place on Earth to launch a rocket? Near the beach. Yeah, scientists like the beach also. Near the equator. Near the equator, because the Earth is spinning. The Earth is spinning. And if you're at the North Pole or the South Pole, you're not spinning, right? You're just sitting there. But as you move out towards the equator, you have a bigger and bigger. Remember, the Earth turns with some angular speed omega. Every point on Earth has the same omega. But the farther away you are from the axis of rotation, the bigger your tangential speed is. So on the equator, you have quite a large tangential speed. Just without doing anything, just standing on the surface of the Earth, you already have some speed. So that saves you a lot of energy. You already have some speed. You can utilize that when you launch, and that helps you in launching rockets and things. Okay, just a quick aside here. You are learning gravity as we teach it in physics 4a. We call that classical mechanics. But Einstein came along around 1905 and said that this is not the way it works, that you don't need two different masses to have an effect of gravity, that one mass can influence another thing that doesn't have mass through gravity. Because our laws say, where are our gravitational laws? You have to have two masses. What happens if one of those masses is zero? The force of gravity is zero according to this equation, right? According to Newton, if one of those masses is zero, there's no force of attraction anymore. Einstein said, no, that's not the way it works. That even a massless object like light has no mass. Even a massless object like light moving through space near a massive object like a star gets deflected because of gravity. And so this is the way Einstein described it. It's hard to picture in 3 dimensions. So let's think in 2 dimensions. Let's pretend our world is like a sheet that's pulled nice and tight across some kind of a frame. And if we come on. There we go. We've got some kind of a sheet pulled nice and tightly over a frame, and we take a heavy object and set it in the center here. And when we do that, what happens to our sheet? It sags in the center there. It gets weighted down in the center. So if you can kind of draw that with like a topographical map would have lines around it like this, right? Indicating that there's some change in elevation there. Does that kind of make sense? Something like that. But a side view would look like this, right? It would look, and here's our heavy object sitting there, right? Weighing it down. Does that kind of make sense? Now, if we have a marble and we roll it in this direction, what happens? It doesn't go straight. The program crashes. It doesn't like that. We have our marble here, and we roll it across this direction. It doesn't go straight anymore. It hits that little valley, and what happens? It goes whoop, just like that. Okay, this is Einstein's explanation of gravity. He says that a massive object actually deforms the space around it, kind of like this massive object on our sheet here. Bent space. Space was nice and flat. We put our object there. Now it's got this warped shape to it, right? A massive object actually deforms the space around it. So any object, whether it has mass or not, traveling through that section of space gets affected by the fact that the space is deformed there. It's a weird way of thinking about it, isn't it? But that's what you have to look forward to in physics 4D. Some weird stuff, mind-blowing stuff. But for physics 4A, we will not think of it this way. Just wanted to give you a preview of coming attractions. For physics 4A, we need two masses to have a gravitational force. Any two masses can have a force of gravity between them, and we can figure out what that is with our universal law of gravity. Question, does the object still think it's going in a straight line? Yeah, probably. Yeah, I think so. It thinks it's going in a straight line. It doesn't realize that the space has changed. All right, let's do this. Let's take a 10-minute break, and then we'll come back and talk about Kepler's laws. We'll just do a real brief discussion of Kepler's laws. I'm not going to test you on them specifically, but there are some problems in the textbook under the Kepler's law section that I think I recommended, because you can do them with other techniques that we're going to learn. You don't need to remember Kepler's laws to do them. All right, 10 minutes. Okay, Kepler's laws. So as I said, I'm not going to ask you any specific questions on Kepler's laws, but it's kind of an interesting story. If you're really interested in this stuff, take one of our great astronomy classes. Question review sessions next week. Yes, I will send out an email. I'll have special office hours, special review sessions. So all the timing changes next week. No classes next week. Our last regular class is Friday. Friday ends regular classes, next week's finals week, but I'll schedule some special office hours and review sessions. The story is that they were trying to figure this out. The ancient astronomers trying to figure out the motion of the planets around the sun. Well, they didn't know the planets were going around the sun, but trying to figure out some of this stuff. And so finally, they built one of the investigators built the most accurate tools of the time for recording positions of planets and stars and things like that. And they had years and years and years of data. And I believe his name was Tycho Brahe. And so he wanted to figure it all out. He had all this data. He wanted to figure it out. But he hired mathematicians and other scientists to help crunch. He'd give this guy a little bit of data, and he'd give that person a little bit of data. And he didn't want to give them too much because he didn't want one of them to figure it out, right? He wanted to be the guy that figured it all out. Well, he died. And Kepler was one of these people he hired to work on it and had some of the data. And for years, Kepler fought the family to try to get access to the rest of the data. And finally, they agreed, or somehow he ended up getting the data, and he figured it out. One of the things he figured out, Kepler's law number one, is that the planets don't move in circular orbits. They move in elliptical orbits. Now, it was hard to figure this out because the planets' orbits are just barely elliptical. They're almost circular, but it's just off enough where if you assume it's circular, eventually your data doesn't make sense anymore. You can't predict where the planets will be because it's not quite right. Now, if you remember when you were a kid, how did you draw an ellipse? You took two push pins, right? And you stuck one here, and you stuck one here, and you wrapped a string around them, tied a string in a loop, and you wrapped it around, and you put your pen over here, and you kept that string nice and taut, and you moved your pen around. And what did that make? It made an ellipse. Yeah, close enough. Now maybe I'll try one more time. Yeah, close enough. That's as good as it gets. It made an ellipse. This is called a focus. This is another one. And the distance from one focus to the point on the ellipse A, plus the distance from the other focus to the point on the disk, on the ellipse, is a constant. So that's the definition of an ellipse. That's why this string technique works. When you're a kid, you wrap that string up because the string isn't going to get longer or shorter, right? A plus B is going to be a constant. As long as you keep the string nice and taut as you go around, you're going to get an ellipse. And as you move those two push pins closer and closer together, what does this ellipse look like? It starts to look more and more like a circle. And when the two foci are on top of each other, when there is only one point there, then you have a circle. So a circle is just a special case of an ellipse. All right. Planets move in ellipses with the sun at one focus. That's the first thing he noticed. And he didn't mathematically derive any of this. He just looked at data and said, how can I fit things to this data? What happens? When does this data make sense? And he kind of realized finally that when it's an elliptical orbit, the data made sense. Second thing he said, I'm not going to try to freehand an ellipse anymore. I'll just pick a tool. Next thing he said was that if the sun is over here, the area, if we draw an imaginary line from the sun to our planet, this imaginary line sweeps out equal area in equal time. So if the planet's moving from point A to point B, that line sweeps out this much area, right? And if it moves from point C to point D in the same amount of time, it has to sweep out the same area. That's what he discovered. So the area okay, he didn't prove anything. He just had lots of data, positions of the planet at, in May, position in June, position in July, position in August, right? He just had lots of data, the most accurate data of its time as to how planets were positioned and how stars were positioned. And he figured out some of this stuff just by brute force, by fitting data and finally saying, oh, wait a minute, it all makes sense when I say this, or I've noticed that this happened. He didn't prove it. So all we knew was that this works for planets moving around the sun, right? Because he just fit that data to come up with his ideas. Later on, Newton came along and came up with the law of gravity, and then you could derive some of this stuff. You could derive the fact that how the planets move. You could come up with circular motion, centripetal force, circular motion, and figure some things out from that. You could come up this idea right here, this idea. What is that? What law did we learn that would explain this? What does it tell us? It tells us that when the planet is far away from the sun, it moves slowly. When the planet is close to the sun, it moves fast, right? That's what this tells us. Conservation of energy would explain that, right? You throw something up into the air and its gravitational energy increases, so its speed slows down, right? Its kinetic energy decreases. When as it falls closer to the Earth, its gravitational energy decreases, so its speed increases because energy is conserved. Same with the planet orbiting the sun. When the planet gets farther away, it has more gravitational potential energy, so it has to slow down. And when it gets closer to the sun, it speeds up. It's falling closer to the sun, it speeds up. What's another thing that might work? Another theory that might work to explain this. Conservation of angular momentum. Conservation of angular momentum, right? I omega. You have something going around. When the radius gets bigger, we treat that planet going around the sun like a point object. So what's I? mr squared. As I gets bigger, as r gets bigger, it gets farther away. Omega has to get smaller. When it comes in closer, I gets smaller, omega has to get bigger, like an ice skater putting their arms out or pulling their arms in. Conservation of angular momentum might also explain this. So now we have two other tools that we can use to derive some of these things and explain some of these things. So what is the point here? The point here is planets go faster. When closer. And our third law, Kepler's third law, because this is an ellipse, this is B. This is A. He figured out that the square of the period is proportional to the cube of the semi-major axis. What is the capital T is the period. That's the time for one cycle. That's the period. So we're going to do, we're going to derive this ourselves. We're going to derive that ourselves, but not for an ellipse. We're going to derive it for a circular orbit because that's what we know how to do, right? So this is a really interesting example. Geosynchronous orbit, in sync with the Earth, right? Geos, the Earth, in sync with the Earth. Oftentimes, we want our communication satellites to have this property. Take the example of you get a dish for your house, you go up on a ladder, you point it at a satellite, you lay down on the couch and you turn on your football game or whatever you're watching, and 10 minutes later, it goes out and you have to go back up on your ladder and reposition it, point your satellite dish toward the satellite again because the satellite is in a different part of the sky now, it's moved. You go back, lay down on your couch, 10 minutes later, you have to get up and reposition your satellite. That is not going to work for you, is it? You're not going to be a happy sports fan doing that, right? What do you want? You want the satellite to always be in the same place relative to the Earth. You want to set your dish pointed at a satellite and forget it, right? Set it and forget it. Walk away and always have it pointing at that satellite. Well, what do? If this is the Earth, this is a top-down view. This is the North Pole right there. And if we're looking down on the North Pole, what direction does the Earth rotate? Where does the sun rise? Sun rises in the east. So the Earth has to rotate this way, right? In order for the sun to rise in the east and set in the west. Now here's some imaginary point on Earth. Maybe that's your house. At the equator, it's your vacation home on the equator. And if we draw a line from through that point, directly above that point, there's a satellite. At this moment in time. What we want to be the case is that at some later moment, the Earth has rotated by a little bit, right? The Earth has rotated by a little bit. And this point is now over here. And where do we want our satellite to be? We want our satellite to be in the same point relative to Earth. So our satellite dish doesn't have to be readjusted. That's called geosynchronous orbit. When the period, the time it takes the satellite to make one revolution is equal to the time it takes the Earth to make one revolution. Okay? So we want to find R for geosynchronous orbit. As you change the radius of your satellite, it changes the period because everything has to balance, right? It's moving in a circular path. We're assuming circular motion here. If our satellite's moving in a circular path, what do we know? We know the force of gravity is acting on it, and that's the only force acting on it. So the force of gravity is providing the centripetal force, mv squared over r, keeping it moving in a circular path. Well, we can figure out that as the radius gets bigger, it changes the time to go around the Earth. So satellites can be anywhere. In fact, I was listening to a podcast one day about a satellite that was being launched. The objective of the satellite was to take pictures of the Earth. They were putting a camera on it. They wanted to take pictures of the Earth. Well, you know what they did? They did what's called a polar orbit. It went over the North Pole, over the South Pole. It went around the Earth this way. And it was close. It was just barely above the atmosphere. Your satellite has to be above the atmosphere or it's going to slow down in the atmosphere and burn up, lose energy and fall in, right? You have to be just above the atmosphere so that you can give it a push and let go of it, and it'll just keep going around forever. There's no air drag. Why a polar orbit? First of all, it's close. You want it as close as you can get. If you're taking pictures of the Earth, you want to be close, right? At that particular altitude, the satellite did an orbit every 90 minutes. Okay, it went around the Earth every 90 minutes. And what happens as the satellite's going around taking pictures? Click, 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 taking pictures. The Earth is rotating. So the satellite's going this way, taking pictures, and the Earth is rotating this way. And the satellite goes around, takes pictures, and the Earth rotates, and it takes pictures, and the Earth rotates. And you can take pictures of the whole Earth that way, and you can get really good pictures. The resolution was amazing that what they were talking about with this satellite. So that's one type of satellite you might have. A communication satellite, where you're setting a satellite dish on Earth pointed to your communication satellite. You don't want to have to move it around. That's a different story. Where do you put that? You put that over the equator. Over the equator at a specific altitude, and it will go around. Its period will match the rotational period of the Earth. So let's take a look at that. The question about the force of gravity. So the force of gravity is here, right? Here's your Earth, here's the Earth. Here's our satellite. The force of gravity is this way. The satellite's speed is perpendicular to that. You give the satellite a push, the force of gravity pulls on it and changes its direction. It's like having something on a string, right? You're swinging it around and pulling on the string, keeping it moving in a circular path. But if this force of gravity is truly perpendicular to the velocity, it cannot change the magnitude of the velocity, right? The force has to have some component in the direction of motion to change the speed of the object. And the force has to have some component perpendicular to the velocity to change the direction. This force is completely perpendicular. It cannot change the speed of the object. It can only change the direction. So what do we use here? Circular motion, circular motion. Sum of the forces in the radial direction equals m times a centripetal where this is r, right? R is this distance. And what is the force acting on this thing? the force of gravity. And as I said earlier, don't fall into the trap, right? This is now is a little tricky because for the first time this quarter, we are dealing with forces that might not be what they were on the surface of the Earth. And a satellite way up in orbit is not experience the force mg. It experiences a force different because it's much farther away from the surface of the Earth. So we have to use our universal law of gravity, G, m satellite, m Earth over r squared. This is force here, over r squared. And this is the mass of the satellite, v squared over r. Turns out the mass of the satellite does not matter. Now we have to figure out what our velocity is. Well, what is velocity? Velocity is distance over time, right? What's the distance and the time? We know something about this satellite, right? What do we know about it? It completes one revolution in how much time? 24 hours, right? One day. That's how long it takes the Earth to rotate one time. So the Earth rotates one time in a day. The satellite has to make it around one revolution in a day. So we have to convert that to seconds. And what do we get? We get G m Earth over r squared is 2 pi r over the period squared, that's v, right? And then we solve, we get some constants times the square of the period is the cube of the radius. This is Kepler's law, right? What do they have up here? Kepler's third law said that the square of the period is proportional to the cube of the radius. Now he said it was more, he did it more specifically, the semi-major axis for the ellipse. But if that ellipse is not an ellipse, if it's a circle, then the square of the period is proportional to the cube of the radius. So we can derive that very quickly for a circular orbit. So don't memorize Kepler's laws, just understand how to do a circular motion problem, which you should know anyway, right? There's nothing new here. All right. A couple of more things with gravity that are kind of interesting. You have an r squared here. You have an r squared here. When you bring that up, this becomes r to the fourth. And then you have an r here, which makes that r cubed, right? Yeah. Okay, so one of the things that we see here, what happens if we go inside of a planet? What happens to the force of gravity? We know what happens as you go away from the planet, right? If you're starting out with some gravitational force on the surface of the planet, as you move away, it drops off as 1 over r squared. Okay. It's a little, try one more time here. How's that? Better? Yeah, okay. What happens as we go inside? If we were to dig a hole and measure the force of gravity in here or in here, what would we get? What would we get at the center? If we had some kind of way of measuring the force of gravity on an object at the very center, what would it be? It would be 0, because there's a little chunk of mass over here pulling on it this way, and there's an equal little chunk over there pulling it that way, and there's a chunk over here pulling it, and there's an equal one over there pulling it. For every chunk pulling it in one direction, there's an equal chunk on the other side pulling it the other way, and they all cancel out. If we're inside of a spherically symmetric distribution of mass, at the center, it has to be 0. It turns out, which we will see in a minute, it increases linearly. In this region. So let's take a look at that, why that is. One of the reasons I spend some time on this, I know you're thinking, when am I ever going to be inside of a planet? Well, one of the reasons I spend some time on this is that charges, the electric force and charge distributions work very, very similarly. The force we get between two charged objects is the exact same equation as Newton's universal law of gravity, but you change the m's to charges and the constant's a little different. It's the exact same formula. And we do go inside of charge distributions and try to figure out what the electric field is and what the electric force is inside of a charge distribution. So that's why I think thinking a little bit about it now, even though we may not use it perfectly now, thinking a little bit about it now is important, because it'll help you a little bit in 4B. Yes, if you dig a deep enough hole. In fact, I put a problem once on an exam. I said that you used to live at the equator, and you moved to the North Pole, and you stepped on a scale, and it read a much higher weight than it did at the equator. So you decided to dig a hole and weigh yourself at the bottom of the hole to get the same weight. How deep a hole would you have to dig to get the same weight that you measured at the equator? Yeah, not very many people got that right. I don't think I'll use that. I don't think I'll use that problem again. But there's a lot going on there. But at the equator, you have to do a circular motion problem. You're moving in a circular path. And because you're moving in a circular path, when you do the sum of the forces equals mv squared over r, you get that the scale is reading the normal force, right? Your mass never changes, right? Your mass never changes, but the scale reads the normal force. And when you go to the equator and you're not moving anymore, the scale reads a much bigger normal force than it does when you're moving at the equator in circular motion, because part of the gravitational force is holding you in that path, and part is the normal force. So so then you just have to figure out how deep a hole to dig to get to match it. Anyway, you can try it if you'd like. the gravitational pull is the same everywhere, right? If the Earth is spherically symmetric, now of course the Earth is not quite perfectly spherically symmetric, but in our problems we treat it that way. If the Earth was spherically symmetric, the gravitational force is the same everywhere on the object, but the normal force is not. What you read when you step on a scale is the normal force. That's your apparent weight. Because you're spinning at the equator, your apparent weight is different than at the North Pole. I think I mentioned in class, didn't I, that there was a boat race, and there was somehow, it was an advantage to have a heavier boat. So they all built their boats up to the maximum allowed limit. And somebody was doing it they built their boat wherever they were near the equator. And then they moved their boat to where the race was being held, and it failed. It came in overweight because it was not near the equator and it weighed more there. Okay, so Newton had to invent calculus to figure this part out, but let's just sort of reason through it. We have a spherically symmetric distribution of mass. That's a big solid chunk of mass. And if we go inside of it, if we're here, we want to know what's the force of gravity acting on us at this location. It turns out that if we draw an imaginary radius at our location, the mass outside of our radius has no effect on us. It all cancels out. Newton, like I said, Newton had to invent calculus to show this. But the stuff on this side, let's say we have this mass over here, there's not very much, is there? But it's really close. It's really close to us. So it exerts a big force. The mass on the other side, there's a lot of it, but it's really far away. So it ends up exerting the exact same amount of force as the green shaded area on the other side. There's a lot of it, but it's far away. The green side, there's not very much, but it's close. It turns out that those exactly cancel out. So all the mass right, the force from the mass on one side cancels out the force from the mass on the other side, pulling. So all the mass outside our radius cancels out if we're in a spherically symmetric mass distribution. The forces, the force of gravity pulling on us cancels out. So it's as if it's not there. The force of gravity due to the green mass pushes, is this thing right here, pulling in that direction. The force of gravity pulling us in the other direction, this one, is due to the blue chunk. Those exactly cancel out. So it's as if we don't feel any force due to the mass outside of our radius, only the mass inside only mass inside our radius contributes to a net force. So if we figure this out, we say the force on us is G times our mass times the mass inside of our radius, that says inside, over our radius squared. And if uniform density then the mass inside, this is going to be the volume inside over the volume total times the mass total. And this is the kind of thing we do this with charges. Little r, oh, it crashed again. Little r is the radius. Let me bring it back. Hold on a second. Little r is our radius, and capital R is the radius of the r, where was I? R cubed over. So this would be capital R, and this would be lowercase r. And what do we end up with here? A bunch of constants. This is m total here, right? M. Bunch of constants times r. So it's proportional to r. That's what I told you up here, remember? I told you it was going to be proportional to r. Now I've shown you. And the reason is, if we think about this for a second, the mass outside of our, if we're in a spherically symmetric distribution of mass, the mass outside of our location is all pulling on us equally and has no effect. We can ignore it. We take the mass inside of our location. And what did we say we can do with the spherically symmetric mass distribution? We can treat it like a point mass at the origin, right? So only the mass inside of our location counts, but it's a distance r away. So as we move away, as we move out from the center toward the outside, the amount of mass inside of our location goes up as r squared r cubed, right? Because the volume increases, volume is proportional to r cubed as we move out. But we put it all at the center and the force drops off as 1 over r squared. So the mass is increasing as r cubed, but the force drops off as 1 over r squared, and you combine those two and you end up with the force is proportional to r. Okay, couple of interesting things we should talk about since we're talking about the Earth and gravity and things like that. One of them is tides. Let's talk about tides. A tidal force, what we call a tidal force, occurs when the force on an object is different on different points on the object. So, for example, if I had I don't know, a water balloon. If I had a water balloon and it was a nice spherical shape, and I could exert the exact same force on every part of the water balloon in that direction, the whole water balloon would start to move in that direction and accelerate, and it would always be a sphere. It would all accelerate together, it would be a sphere. But if I had a tidal force, if I pulled on one side with more force than I was pulling on the other side, my sphere, one side's getting a bigger force than the other side. My sphere would start to move, but one side would accelerate faster than the other side, and pretty soon my sphere would look like an oval, right? Would look like a football, an American football shape. So it would get stretched out, elongated as it moved in that direction. One side would be accelerating faster than the other side. Well, what happens with the Earth is that the Earth is so big, the force of gravity on one side of it, due to the sun or the moon, is bigger than the force of gravity on the other side of it. So it gets a slightly bigger force on one side than the other. And what happens is it ends up getting a little oval shaped because of it. Except that the Earth can't really stretch. The Earth is pretty solid, can't stretch too much, but the Earth has this liquid coating around it, right? The oceans, and those can stretch much more easily. So we end up with this situation. Let me see if I can. Yeah, close enough. Yeah, not bad. So if this is the Earth, and this is the ocean here, I'll use blue. It's this is the ocean. And we've got the moon over here and the sun over here. Then we get this elongation that takes place, right? You see that it gets stretched a little bit in one direction. So the Earth is when the pull from the moon and the sun are in line with each other, we get our maximum tides. It doesn't matter whether it's like this or whether we have the moon over here and the Earth and the sun. Doesn't matter. As long as they are in line, as long as they form a line, we get our maximum tides. Come on. When they form a 90-degree, then we get our minimum tides, right? You can see that if the sun is pulling in one direction and the moon is pulling in the other direction, they kind of cancel each other out, right? When they're both pulling in the same direction, their effects add together. All right, so let's think about why this is. And so this is kind of a top-down view. We're looking down at the North Pole. So what happens? We have a point on Earth here. And at some point during the day, we look down, at some point during the day, that's a very thin layer that it's passing through an area where the ocean is not very deep. And as the day goes on, that point on Earth now becomes over here somewhere, passes through a point where the oceans are deep. And a little later, it's over here somewhere and the oceans aren't very deep there. And a little while later, it's over here where the oceans are deep again. So the water gets stretched, the Earth spins, and point on Earth passes through high tide, low tide, goes through. You can see how it goes through high tides and low tides as the day progresses. All right, let's think about which one has the bigger influence on the tides, the moon or the sun? We have any surfers? Any surfers in the class? They're usually experts on tides. Which one has the greater effect on our tides, the moon or the sun? The moon does, that's correct. Which one exerts the greater force of gravity on the Earth? Is the force of gravity between the Earth and the moon greater, or is the force of gravity between the Earth and the sun greater? The force of gravity between the Earth and the sun is much greater. Yet the moon has the bigger effect on our tides. Let's see why that is. If we were to plot, I've got 2 minutes. Okay. Force of gravity versus distance. And so we're at the surface of some object, and we get, what do I have here? Let's call it F0. At the surface of an object, we measure a certain force of gravity. If we double the distance, what's the force of gravity? One quarter as much, right? It goes as 1 over r squared. Double the distance, you have 1/4 the amount of force. So if we started out here, now we're here, right? And if we triple the distance, we're 1/9. 1/9 is about there. And if we go 4 times the distance, we're 1/16, right? Right about there. This is hard for me to draw, but and this just eventually, right, becomes smaller and smaller and smaller, right? Now, what matters is the delta F, the force difference between one side of the Earth and the other. Even though the sun is exerting a really big force on us, the sun is far away, right? So if the sun is far away and I draw the Earth over here, the Earth, let's say the Earth has this much distance here, some planet, then from one side of the planet to the other, out here, I've got a delta F of this much, right? But if I draw my Earth over here, from one side of the planet to the other, I've got a delta F of this much. Even though it's exerting a smaller force, the moon exerts a smaller force because it's so close. We're at that really steep part of that 1/r² drop off. And so the delta F from one side to the other is much more than from the sun, and it contributes more to our tides. Okay? That's a good place for us to wrap it up. I'll stick around if there are any questions. I'll stick around for a little bit, but I'll stop the recording now.